from IIT Kanpur, and he did his PhD from PRL in 1998, and he did his postdoc from University of Washington and in Illinois. And his area of interest is quantum optics, nonlinear optics, coherent control, mathematics, etc. Now I invite Professor Wanare to come and give it.
Ranjan, for thinking about us. Okay, it's a pleasure to talk to students anytime. This is going to be like a class, okay? Yeah. And because I was told that there has been no great discussion on nonlinear optics per se, so feel free to stop me at every point. The more you stop, the more you learn, and the more you see the speaker troubled, you'll enjoy it more, right? So your job is to pin me down and see whether I survive. So feel free and stop me anytime. All right. So what I have here is a summary of what I'm going to say, but there are a lot of inputs which I will put in, and all that I will talk on the board. So just in case you ask anything, explanations will be on the blackboard. Oh, 1 second. Okay, so this is my original talk was on coherent processes in nonlinear optics, and then I was told that no, just do nonlinear optics and basics. So that is what I am going to do. So probably the first part of it is going to take as much time as you want, and I will quickly go through this part, which will not be too much. So the idea is first to understand what do you mean by nonlinear. What is nonlinear about optics? Then there is this notion of coherence, which is very, very important. So I will discuss about the usual notions of coherence. I will define what it means, try to understand physically what it means. Then we will look at coherence in the electromagnetic field itself, okay, which is related to something called spatial and temporal coherence. There are some other things like higher order coherence. Then we will look at coherence in an atom. There is a difference between probability amplitude and probability itself, okay. So this notion of coherence comes in there, and then you put both of these atom and field together and see what is coherent about it and what kind of coherent phenomena this gives rise to. So I am going to go at the simplest of textbook examples, okay, and I cannot touch upon my work simply because maybe tomorrow I will manage in some half an hour. But let's see how it goes. Okay. So please stop me whenever you want. Somehow it's not responding to what I do. Oh, it does. Okay. Yes. Okay. So nonlinear optics, we begin with what describes a wave, right? You have the 4 Maxwell's equations, and once you write down the Maxwell's equations, you make some simplifying assumptions, and then you come to some simple forms, and eventually you get something called the wave equation. I could have just said that, shown you 4 equations and job is done, so but I will not do that, okay. So you see that I have chosen to write down this business with 4 vectors. There is a H field, there is a B field, there is a E field and a D field. They are all relatives in the sense that H and B are intimately related, D and E are intimately related. Now the point is, these equations describe Maxwell's or electric and magnetic fields inside material media, okay. So if I write down these equations in vacuum, I will not have to worry. There is no need to introduce these new vectors. You must be familiar with, without the D, without the H, you know, without them one could write it in vacuum and be done with it. But you see, we don't want to do that. Why is that? Because one of the most important why Maxwell's equation is so powerful, because the interaction with material, it is able to, I will use the word parametrization. Parametrization. That is, I will solve the Maxwell's equations whichever way I want. Or you bring me glass, I will put the numbers for glass. you bring me another material, I will put that number. So all that I will do is I basically vary parameter, and parameters are the huge class of materials I have, and all of them need to be described only by these 4 equations, and all that I have changed is merely the parameter. So it's this parameterization which is what makes Maxwell's equations so powerful. Okay, and they are applied almost everywhere. You fall on the ground, you get hurt, it is Maxwell's equations. With apologies to Asima, it is not biology, it is Maxwell's equations. Sorry. You know why? Because why do you feel pain? You have, so there is obviously repulsion between charges. I can't go and, if I hit my hand on the board, the charges there are going to repel my charges here. And at the end of the day, it is electrical signals from my neurons that go and hit and tell me, oh, it's pain, and I feel pain. So it is all Maxwell's equations. So they actually dominate. Yeah, don't hit me, it still pains. So you see, Maxwell's equations are valid almost everywhere. So if you look at length scale of where it is valid, you get light all the way from galaxies. I mean, so that is hundreds and millions of.
You can use pointer.
I can use this. Oh yes, thank you. I'm pretty bad at technology, but it's okay. Physics people have, you would find your older teachers, I mean the teachers from whom I learned, they would never use this PowerPoint presentation. They will write it out, And physicists are responsible for invention of almost everything under the sun. I can say it aloud. Internet is our creation, but we don't use it. We just make it for others. Okay. Laser also. Okay. So now the validity of Maxwell's equations across all scales. Okay. All the way from, if you just go step out of the nucleus, that is about 10 power minus 15th of a meter from the center of the nucleus, just walk out of it, you will see that Maxwell's equations switch on. Near to that, there will be nuclear forces. Let's not worry about that electroweak interaction. Okay, but when you step out of it, it's electromagnetism all the way till the end of the universe. It's Maxwell's equations. That is the most dominant thing. Of course, gravity takes over at much larger scales, but the point is, it's a phenomena that is very, very varying. So now what we want to do, because we want to utilize the idea of parameterization, we go from a microscopic description of E and B fields to this macroscopic set of equations. So what one actually does, if you recall, I'm sure you have seen derivations of Maxwell's equations. For example, the first law would be del dot E is some rho over epsilon naught, right? You recall this. So what I do is something very neat. I say that I understand that there are 2 kinds of charge densities inside material. So I separate it out, say that this is rho free plus rho bound, right, by epsilon. I have done this, quite smartly, because I understand that when I pass a current inside a wire, I mean free chaps. But the wire is made of some guys who actually respond to electric field. They give a channel, for example, for this thing. So that is there in rho bound. And one can quickly make out that this rho bound is related to something called the dipole moment that you create. So what is this notion? Notion is that I have an electric field. Moment I have an electric field, something which is neutral, electric field will push the positive charge away, so you create a dipole moment. And then you count the number of dipoles per unit volume, you call that polarization. So definitions are very, very straightforward. It is not something that you come about it's not an unnatural concept. So you have dipole moment per unit volume, you find out that is your polarization. So now you can see clearly, for example, I have a block of material. This, let's say, is my x-axis. I have a block of material of length L, right? It has got a dipole moment. That is, I had applied some field, let's say, and it accumulated, it responded to this field and it separated the positive and negative charges. So what will happen is minus plus, you see that all these dipoles get aligned. It's a one-dimensional problem. So you see that on one edge I have all minuses, on the other edge I have only plus. So you see what is happening within the material, plus and minus are getting cancelled essentially. What you have is a remnant. There is nobody to cancel this minus on this edge, and there is nobody to cancel the plus on the other edge. So you say you have a remnant negative charge and a remnant positive charge. This is precisely bound charge. Okay, so if you see, so if I plot out my polarization, if I look at dp over dx, it's a one-dimensional problem, so it's a total differential. There is a change in p. So what is it? If I plot the dp over dx, you will see that, oh yeah, I suddenly smoothen this out. So you see that my dp over dx has changed, right? It is 0 again because it's a constant. And then on the other edge again it is a dip like that, that is going to be dp over dx. And bingo, put a minus sign, that's it. This is your rho bound. Because minus is precisely, minus of dp over dx is precisely the charge you have on the one side, and plus is precisely the charge you have on the other side. So you see that spatial variation of polarization effectively comes out as bound charge. So you see that this is the guy I do, and I put this, so I write this, I won't mind a cloth. कपड़ा मिल जाता है तो थोड़ा सा आसान हो जाए. So you see that here I can replace this by minus del dot p. Okay, so what do I do? Yeah. Oh, your handkerchief.
No problem.
Okay, thank you. Very generous. So okay, so this becomes, you see, epsilon naught E plus del dot P. This equals rho free. And this is what I have done. What I have done is del dot epsilon naught E plus P. This equals rho F, and that is del dot D equal to rho F. That's my first equation. Right? This is what is Coulomb's law. So you see, my ability to separate out polarization into something which is bound and something which is free makes me step from microscopic level to a macroscopic description of material. So now I am associating a number. Otherwise, I have to worry about if I am inside of a microscopic. For example, I am sitting at one point. There is a nucleus here. There is an electron there. It is coming this way. I have to worry about how it changed. So I am going to get a total mess because it's going to be very awry. What we have done is we have stepped out of this microscopic picture and associated a parameter. That parameter is precisely what is this polarization. Okay, I will come to that exact parameter soon, but that's what is polarization. So this is what is the jump from microscopic to macroscopic. So the first is called the Gauss's law, the first equation. It tells you that, rather in this form, it tells you that if there is a finite divergence within, so you understand divergence, we can actually write this force set in integral form. I'm sure all of you are familiar with that. And what it tells you is basically it's a counting problem, and it's also a strange non-local thing. I have a region where whose volume, in the volume I sit down and calculate del dot E everywhere. Okay, let's look at this. Easier to forget about bound and free, but you just calculate in a given volume del dot E at every point, add them up, that is your integration over volume, and then you calculate the flow of this electric field only at the surface that is bounding this volume, right? Add them up. These two quantities are strangely equal. This is called the Gauss's theorem. So you see that what it is telling you is that if there is a net flux, that is net outward flow of electric field, which is just fluxes, something you calculate over surfaces, right? So net outflow, if you have, then if you have finite net outflow, then you say that there is a net charge inside this volume. If this is equal to 0, implies there is no net charge inside the volume. This is what is Gauss's law. This also results in the fact that the Coulomb's law is 1 over r square and all that business. So that's all hidden here. Similarly, del dot B is telling you that there are no sources of charge for magnetic field. That is, every time you take a closed surface, B out and B in will exactly cancel each other. Right? That's what it is telling you. Because if it didn't cancel each other, there will be a finite value on the right hand side. That is what we associated as rho, charge density in the other case. Here there are no such charges. Every time B goes out, it comes back in. So that would mean that del dot B is 0, or there are no magnetic monopoles. So that is Gauss's law from the, for the magnetic field, if you want to call it that. The third one is Faraday's law. Okay, Faraday was an amazing experimentalist, did variety of stuff. Actually, almost every time I I'm teaching a new course, I'm finding that Faraday has done something there. So it is, he has done in such many areas. So for example, estimating the size of sizes of molecules, sizes of atoms, differentiating between atoms and molecules, looking at sizes, estimating their actual size to get to Avogadro number was done by Faraday. You would believe that? So apart from this electric field which you know. So, okay, so what is this law? It is telling you that if I have a region where I change magnetic field, then this change of magnetic field is not liked by that region concerned. What it is going to do is going to